This presentation today is specifically put together to address some of the latest development in KUBRIX, but also in the use of Rhino alongside KUBRIX for the generation of complex models. There are currently nearly 60 to 70 Rhino users within Itasca itself. Not all of them use KUBRIX for and Rhino for mesh generation. They often use Rhino for measuring dimensions on their models. However, there is a relatively large community of users, and these users have developed new methodologies and new approaches, many of them new to me, but there are different approaches that during conversations and during support sessions I find out about, and I would like to share some of those practices in this presentation today. I will proceed here. The agenda today is to speak about an update on the latest tools, time-saving tools, and best practices that are available to us in the use of Rhino for specifically the use with KUBRIX, but also with any other approaches, for example, approaches within the FLAG3D and 3DEC tools, or approaches involving preparing surfaces for ranging and so on. This webinar is being recorded at this time, so you will be able to get access to it. What is available today within Itasca in terms of what we call, in general, grid generation tools? There are a variety of tools that are available. Of course, since the beginning, the GenZone command and fish functions and all the very creative ways that people have used these very low-level programming tools to create very complex models, because since the beginning of time, both FLAG3D and 3DEC were highly over-dimensioned software. They were capable of doing a lot more than what the model preparation tools were allowing them to do. So, GenZone, commands, fish, 2D extruder since 2012, the topograph standalone command, which allows you to create a boundary-fitted topography, the densify command, the geometry range, which allows us to create a stair-step mesh and then select part of the zones or part of the blocks as various geotechnical units or various shapes. The zone splitting capabilities, whether the one that is already in FLAG3D or the one that is in KUBRIX, or the one recently put in place by Jim Hazard in TET splitting, which is a very elegant method. And then finally, another tool that is available, many have different versions of it, fish functions that allow you to move back and forth between FLAG3D and 3DEC. In particular, going from a FLAG3D model to a 3DEC model, so model of zones in FLAG3D that becomes a model of blocks in 3DEC. These are important because FLAG3D offers a grid infrastructure, whereas 3DEC does not. What does that mean? It means that when you ask FLAG3D to draw a plot item for you, what is drawn on the screen is the boundary of the zones, so the zones that are free, the zones that have no neighbors, the zones that are at the edge of two different materials. Whereas in 3DEC, all the blocks and all the faces belonging to all the blocks are drawn, so it's very difficult to distinguish various shapes. So certain operations, such as hybrid mesh building, are easier to do in FLAG3D and then translate into 3DEC. Some of the current and upcoming FLAG3D and 3DEC model building capabilities are also shown here. the topograph, as I mentioned earlier, but also the building block maker, which will allow you to do essentially 2D extruder, the equivalent of that. But of course, it's a more challenging problem, and the ergonomics of it are a bit more complex, but you can see that you will be able to create shapes that look here a little bit simplistic, but will be able to handle curved shape. So essentially, functionalities similar to what you see in Block Ranger today, but with the ability to script them as commands or as fish commands, and then later on vary them or parameterize them and so on. So that would be very, very useful to have in our quiver. I have a picture here that Val Schmidinski, who is the current developer of the building block builder, gave me. It represents a collection of basically a single block, grid points on it, or a collection of blocks whose corners are being carried over a sphere, so being adapted to a sphere. There are many more things about this tool that I'm sure software people would be very happy to bring it up when the product gets closer to release. The agenda today is a little bit, what's the word, ambitious. I was very ambitious when I put this agenda together, so I put in there some items that I may not be able to address today, but what I would like to suggest is that anything that comes to your mind in the meantime, or any question that remains unanswered at the end of this presentation, which I'm sure there will be many, I would like to invite you to please send me an email, and I will include that in my next I will include that in the recorded version of this presentation. The purpose of this presentation is to create a community of people so they can exchange information about all the various schools of model building within Itasca. That we found to be very, very important, because people are all using certain practices, whether it is people in Sweden as compared to people in Australia, opposed to folks in Santiago, or folks in Sudbury, or people here in Minneapolis. We all can learn from each other, and there are certain best practices that I think everybody has now converged around until improved tools appear. Obviously, we have a collection of many tools, none of them really 100% ideal. So I will be talking about automatic versus interactive meshing, and new problems and new tools, and then I talk about new surfacing, new approach of using surfaces instead of meshes, and then choice of surfacing technology, and then as time permits I will tackle some additional questions. Again, please feel free to send me your questions by email afterwards. Automatic meshing versus interactive meshing. In this group today, among the participants, I can see that there are practitioners of Rhino, KUBRIX, but also folks who may be seeing this for the first time. Essentially, in short, in automatic meshing, you create a triangular surface and you tell KUBRIX to fill the inside with hexa or tetra elements. In interactive meshing, you create in a similar way as to the command process of the geometry of the zone command. You create blocks that interactively and graphically in Rhino that then you tell KUBRIX to, or Block Ranger in this case, to turn into collection of zones. So I will show here a quick video, canned video I guess, of what automatic meshing is all about for those who may not be familiar with that. Essentially, I'm showing here a mesh of a geological unit that has been made into rectangular or triangular elements, and inside of it there is a fault that is in blue, and I have already exported these files as STL files, which I will explain, and I clicked on the icon marked KUBRIX, which is this little icon on the left side. The KUBRIX console window is right now running on the screen. The program remeshes these triangular surfaces, which are originally very kind of straight and Cartesian, and turns a mesh at the end, which describes how many blocks are in there, and also describes the 10 worst elements of this model. And it produces also a log file that has all this information, so you can grab information from this log file in terms of remembering what's the smallest edge. Here I bring up FLAG3D, in which now we can actually go into File, Open, and directly read the mesh file produced by KUBRIX, which appears as a .flag3d file, and you can see the mesh now on the screen. It's a tetrahedral mesh. I would say probably the least desirable of all the elements that FLAG3D can accept. And you can also look at, sorry, it seems to be that, okay, you can ask for face groups, and you will find out, and I will stop here this video for a second here, you will see that in the plot item there are zones which I have hidden, and there are face groups which I have left open, and you can see that there is one face group whose name is incidentally f.stl. f.stl was the name of the file that I indicated as a fault in my KUBRIX command line. I just put all of these faults into one single STL file, and as a result, in KUBRIX version 15, you will get one face group called f.stl. So if that face group will have certain properties, you can do things with it. It's not exactly practical. It's best to subdivide these faults into different faults and say dash fault f1.stl, f2.stl, f3, but we will see that a little bit later. So I will continue this video. You can see that these face groups appear on in the plot item. In interactive meshing, I would like to show you what we can do. We create a collection of blocks. This is an example that one of our colleagues has created in Rhino. As you can see here, we have a collection of solids in the sense of Rhino, closed manifold surfaces that have been created. And as you can see here, I've colorized them based on their various layers. There is a layer on the right called outer, a layer called outer 2, and a layer called inner. You create these blocks and you organize them into different layers, which will later on become groups in FLAG3D. And you run Block Ranger, which is the next icon here. It's very simple. Just by default, you click on it. Of course, you have done all the work in advance by making sure that these blocks coincide. And that is explained in a number of tutorials. But once you have done that, a FLAG3D file is created, which you can see here is a collection of several tens of or 100 zones. But if you ask FLAG3D to color it based on slot 2, then you will find out that the layers that we had in the Rhino model have become now FLAG3D groups. So this is very practical to organize your model. Another example of interactive meshing, and so is essentially coming up. Okay. In this other example here, we are producing a 3-deck model. So the 3-deck model essentially is a similar operation than the FLAG3D model, except that you choose a 3-deck output. And I'm bringing up here the 3-deck model. It takes a little while, but what you can understand is that 3-deck model is a collection of commands, and so it's reading that. And when the 3-deck model is read, you will see that the resolution and all the sort of zoning information that you enter in Block Ranger become essentially the way 3-deck discretizes curved shapes. So you can play with that. If you don't want to create too many 3-deck blocks, you can reduce that number to default values. You can change all of these things. So now I want to talk to you about how interactively we can modify this. As you saw, this model was created with the number of default parameters that the program gives you. What would be interesting, of course, is to be able to have some more control. Okay. In this example, the same example, we're going to look at the interactivity of model building. You can see these are all global parameters that were used in here. Now I would like to go in a particular area and change the model resolution in there. And so instead of going directly to Flag3D, I'm importing the WRL file into Rhino, which is also produced as a result of the meshing process. And I colorize it, and I look in particular around in the crown area around this hole here, and I see that 3 elements across. That's not very good. So what I'm going to do is that I clicked on this icon here in the KUBRIX toolbar group, and which is essentially the duplicate edge command, and I say select this edge, select this other edge. I want this edge to be set to 5. This new edge, I want it to be set here on the right to 6. In the name field, I'm putting the number 6, which means that I want this edge to be subdivided into 6 zones or 6 blocks in the 3-deck lingo. Here again, I selected this edge, and then another edge below it, and then another edge below it. I am selecting all these edges at the same time, and collectively on the right side in the name section, I put 10, which indicates that I want these edges to be discretized with 10 elements. So I can select the entire thing. It would be nice to remove the mesh, select the entire collection of solids, but also the curves that now bear an information, which is the edge resolution. So I select the entire collection, so you will be able to see here what these curves look like. You can see on the right side in the name it says varies, but if I select one of these curves, you see 5, the next one you see 6, the next one on top you see 10, the one below it you see 10. So I have assigned these things, I select them all, and I run Block Ranger by clicking on that red KUBRIX icon. Block Ranger runs, and immediately we will be able to read in the WRL file, which is an interpretation of our wishes, which comes up here. I immediately colorize it so that I can distinguish the various groups, and if I zoom in that area, I will see that indeed that resolution has been set to 5, the next one to 6, and if I step farther back, I notice that my various layers here have now turned into 10 blocks or 10 zones. So this is very attractive both for Flag3D and 3-deck. Of course, this type of interactive meshing is often complex because it has a tendency to produce many blocks, so a lot of shapes may not be very amenable to this few number of blocks, so very organic shapes do not lend themselves very well to this type of treatment. Here you can see the Flag3D model. Again, with the resolution, I have changed it to colorize based on slot 2, and you can see that in the neighborhood of that shaft there, the mesh resolution is more acceptable. Many of you, of course, are also used to the command called, to the control parameter called ratio, which squeezes or biases the mesh in various directions. That will become available very soon. The purpose of Block Ranger is to provide a tool that is repeatable and easy to use, where we use the best of what we can do with KUBRIX, best of what we can do interactively within Rhino. So here I have an example that is very interesting. Maybe it would be best if I showed you here, and I'm doing a live example here. I am going to show you a mining example involving a model that has been created with Block Ranger. This model is a mining example that shows the power of a tool such as Block Ranger, in which what we have done, basically we have a mine plan here. If I show a top view here, you know, you have a mine plan that you may be very familiar with, this type of shape. You can create this shape, essentially a bunch of polylines on a flat, perfectly horizontal surface. Here I tend to use straight lines, but you don't need to use straight lines. You can use more complex lines that are Bezier curves, which Rhino calls curve freeform. Okay, you have control point based freeform or interpolate based freeform curves. But all this to say that these are so-called single curves, simple curves, curves that you cannot explode. So you can use these curves to describe faces that then will become faces of a block ranger block. So I created this shape, and essentially then what I did is that I took all these curves and I said surface planar curves. So each of these tiny little surface areas became one single face, either quadrilateral, but also a few triangular oddballs that you can see in here. Here, for example, you have a triangular sort of surface. Anyway, once the surface is extruded perpendicular to in a vertical way, you create basically as many solids, either hexahedral solids or prismatic solids that go all across down here, and you can actually mesh this object interactively very quickly with Block Ranger. But what is interesting in here is that we also have a couple of internal horizons that we used for this model. And so what we did is that you could have, I could bring up the horizons which were used in here to slice this model at these are actually two different horizons, not the ones that we used, but all the same, you can slice this collection of vertical solids with two surfaces using the solid Boolean split, which will give you then, turn each column into normally three solids, and all these, you select all the solids and you can use Block Ranger to mesh them, and you will obtain a very good quality mesh with a very controlled distribution of zones. So this is a very, very nice and attractive, and we've used it a number of times here at Itasca. The generation of this mesh is usually less than a day, typically less than half a day if you have done that before. If you haven't, maybe it will take a couple of days. Okay, so I'm going to get out of this particular example, and I'm going to move to the next chapter, next point, new ways to do things, a compilation of so-called best practices proposed by model builders at Itasca. There are, a dozen people at Itasca who build models almost on a daily basis, and then a lot of other people who dabble into that. And obviously, there's a lot of expertise that goes into this model. It's not exactly academic, but it's certain skills that requires, being able to see 3D in space and remember commands. And not every engineer has the time to focus on that. So obviously, we are moving towards a distribution of labor, meaning people who will be doing some of these things, and then people who will be working mostly with the actual solution approach. So we are in a transition period, so we all have to know a little bit of everything. Now, the next topic that I would like to approach now is, we are halfway through our presentation, is essentially moving away from manipulating meshes as we did before, instead of manipulating surfaces. What does that mean? Meaning that, first of all, intersecting meshes, because meshes are distinct entities, intersecting meshes brings in the notion of accuracy of the coordinates of the grid points that are on these meshes. If you are using a surface, there are accuracy issues, obviously, associated with the control points, but somehow, genetically, Rhino has better developed in terms of surface manipulation than meshing manipulation. Surface has always been there. Issues of surface tolerance has always been there. Issues of meshing tolerance have not been there. And in fact, many CAD systems don't know how to deal with meshes very well. So we are going to go towards them by turning everything into surfaces. And then I'm going to describe how we use before we use the non-manifold merge then at these surfaces, then to make sure that these merge surface is valid, we're going to use this particular command called test extend slits, and I'm going to click in here. There's a little AVI that I'm going to run here, what I mean by these test extended slits. So this is a model that we did according to the book, meaning everything was a surface. I'm going to remove the box, calculation box. There's a topography in there. It was obtained by some draping process, and I'm going to go into detail about how we surface this object. And then I will select all of these, select all these objects, and then I say copy. Keep a copy. Okay, nothing happened. So far, I just kept a copy of this thing. And then I clicked on the command. The old icon for merge breps now uses the non-manifold merge command, which is a gift from heaven, because what it does is that it produces a really, at first, very ugly, but later on very pretty non-manifold surface that can be meshed with very few problems. So look at this shape now, what it looks like. It looks a little bit decrepit. Some parts of it are transparent, some parts of it are opaque. This is a telltale sign that this is a bad geometry. If I do a check, it says this surface is not valid. And the reason it's not valid has to do with the fact that some of these surfaces have been cut, not all the way through, so topologically they cannot be represented properly. So I use this command called test extend slits, which has been made for us, for Itasca, and so which will be part of the complete offering of the Rhino people. But now we have an object that we have created, except it has wings, that is valid. So this is a non-manifold, one single non-manifold polysurface that is valid. Of course, now we're going to have to prune this thing. Pruning meaning sort of what you do, I guess, I don't know, in the fall or in spring, when you take the leaves or some branches off the tree. We're going to talk about that. Prune using extract surface. So I'm going to bring up the pruning process. So you're going to see what the pruning process looks like. I'm going to try to keep collected here. All right. So as you can see, I copied the previous surfaces because the identity of the previous surfaces was lost during the merging process. By now, pasting back those surfaces, they all have gone into their respective layers, and I have turned off the layers, so that information is still there. So we haven't lost the original one by doing this copy. So I go to extract surface, and I click on everything that is outside, by strategically aligning myself with the walls in various directions. I get rid of all these additional, surfaces that stick out of my model. And this is kind of boring, so I'm going to go forward here, in the interest of time. I continue pruning. There are little bits and pieces that stick out, etc., etc. Now I obtain something that looks pretty cool, and it looks very nice. So this is my non-manifold model. This is what I would like to hand over to KUBRIX. Oh, there's a little thing sticking out of there. I would like to hand over this to KUBRIX. Of course, I have to mesh it because I don't want to let KUBRIX interpret the surface. I want to give it a collection of triangles, validate the triangles as what goes into KUBRIX as a description of the surface. So once this has been done, we have a nice non-manifold closed surface that is totally ready for being meshed. Okay, so there's some more pruning, obviously, above the topography. You can see that all that information that I had copied there, pasted in the back, is still there. So now we have to prune everything on the top. So I'm going to go real quick in here. So basically, I'm removing the top. I don't want to mesh. I mean, if I wanted to mesh an excavation from the top, I could have. But what I'm doing here is that I'm removing these extra surface patches here that we have. That non-manifold surface that we had originally remains one single non-manifold surface. So everything I remove still remains a good candidate for KUBRIX, albeit not necessarily practical. So I keep on removing all these other bits of surfaces that stick out. Just remember that sometimes it becomes very hard to see And I think one good way of doing that is to use the various shading functions that are available within Rhino to see this thing. You know, this becomes complicated at some point. So I'm using the flat shading, then I'm going to go into some sort of a shaded rendering here. That is a good way to see abnormalities on the surface. You know, there are tools available within Rhino, and designers of surfaces, designers of consumer products, and so on, do use these tools to find out whether the surface is good enough, and you know, we need to use that too. So the next operation that I'm going to do, I'm going to ask you to show me the naked edges, if there are any naked edges on this non-manifold surface. It's a good thing before you even mesh it to see if there are certain flagrant sort of very obvious naked edges on this. So I select this non-manifold surface, and the same naked edge command that you have that works for meshes also works for solid surfaces. And you see a bunch of naked edges, but nothing to worry about, because these are actually intermittent faults that are inside our model. So you can see that these are there for a reason. And since they are read in KUBRIX with the -fault command, KUBRIX will not balk and will not throw an error. So that will be acceptable. Now we're going to mesh this thing. So I'm going to bring this up now, the meshing process. Okay, so now we have this nice poly surface. All the reason we did this is to mesh it. Obviously, we use the meshing command. You know, the notion of density is important. The notion of minimum quad is important. I'm not going to go into detail of that. But simply at this time, and while the solid is selected, I'm going to put it into a layer called poly surface just to get it out of the way and hide it. So now what I will be able to see is just simply the mesh. And this mesh, if you selected it, you would see that it has very, very, very few problems, which is the whole reason why we're doing this. Now I'm going to go into a really, really interesting part, which I have discovered lately, and I'm sure many of you may have discovered that on your own. That makes life really, really, really easy in separating this mesh into various components. Okay. All right. So this is our mesh, and as you see now, in terms of handling our mesh, you know, so okay, I think I will talk about that example a bit later. But in this model here, I have separated the various pieces of mesh corresponding to those surfaces, to the original surfaces, original layers, to different groups, and I run KUBRIX by putting -fault f1.stl, -fault f2.stl, -fault f3 all the way to the end. And when I run that, KUBRIX reads these different faults. And so I will go back to how I separated this model. I hope I will have the time, or else it will be the subject of a future presentation. But KUBRIX runs and says that there are a number of interfaces in there, 7. Actually, I forgot one here. You see 9. There are a couple here that I've forgotten. But it also mentions that, I'm going to maybe stop this real quick right here, just another bit of information for you. So in this model, we've separated the outside mesh from the inside meshes, and we put everything that has boundaries and free edges, faults, intermittent faults, and later on, you could include all the sides of the model, east wall, west wall, north wall, I don't know, a boundary on which you assign a piezometric, you know, hydrostatic distribution of pressure. All these groups of faces in the final flat 3D model or 3-deck model on which you're going to do something, you can turn them into groups within Rhino already. So they become different face groups, which then later on essentially takes away any need for manipulating ranges with coordinate systems. So it reduces the size of the data file considerably and makes life very, very easy. But that information about where you're going to apply the boundary conditions, where are the boundary conditions on which you put, to say, hydrostatic, where's the east wall, where are the boundary conditions that are going to be on rollers or those that are going to be fixed, that information is already known in Rhino. We already know that. So we can do that there. Name it even there as east wall, west wall, and they will appear in Flat 3D as face groups called east wall, west wall, or face groups that will be promoted as interfaces within Flat 3D. So that way of working, which is my personal way of working, I think maybe has some merit, and so you can do that. And also what you see here, that KUBRIX reports the 10 smallest tests. We are using the notion of small as an indication of the notion of quality, which is not fair, but there are some issues with what really quality is. But it says that the 10 worst go from 10 to the minus 8 to 210 to the minus 7. So a tenfold change in quality occurs within the first 10 elements, which means that if we improve these 10 grid points, then we can expect to improve also our time stepping within the model. So a little work, again copying and pasting these XYZ coordinates into Rhino after typing the points command will bring up those points, and then you can zoom in exactly in that area and see, oh my God, I have an element there that is the result of a fault coming very, very close to a surface, and that is creating a very small element or a bad element, which is going to later on cost me in terms of CPU time. So let's merge these two nodes together. Let's get rid of that. That is not vital, etc., etc. And you can then correct these things without any loss of generality and gain maybe an order of magnitude. Sometimes you see in the first 10 worst elements, you're getting 2 orders of magnitude of improvement in the volume, which may result to almost sometimes 1 order of magnitude in speed. So I'm going to continue here. So all that information remains as I see. Grab it here and put it into Rhino, and so improve the quality of your mesh. So I'm going to move on here to the other part, which is surfacing technology. It's a very kind of a big word, but really what it tries to say is essentially whether or not what are the tools that we have available to us today to create these really pretty surfaces that we saw. Okay, well, first we said we want to stay away from using meshes. Okay, we get everything as meshes from our customers. Everything is mesh, you know, because it comes from Vulkan, it comes from Leapfrog, GoCat, everything. So how do we deal with that? So we see a number of familiar tools in here: Loft, Patch, Mesh Patch, Drape, and then some Edge Surf is another one, and then some combination thereof. So let's go through these things one by one. So I'm going to click here on the Loft example, and that will bring up Rhino in front of me. All right. Here's Rhino. I have an interactive session of Rhino. So somebody gave me this. This is not exactly as clean. This is way too clean for some of these faults. But as you can see, these faults, all these faults have certain physical features. First of all, they're like curtains. You know, there's a direction in this direction where things vary very quickly, and then there's a direction sort of top down, where basically these things are hanging. You know, this has to do with the the geological history and the morphology, how the morphology was created. But at any rate, we can certainly exploit this by saying, okay, I'm going to take this object, I'm going to duplicate this border. I like to combine commands with that. So the border has been duplicated. Now I'm going to just keep the border, and then I'm going to say this object here, I'm going to make it big, and I say split this at those corners. So I'm going to say edit, split, and I like split point, and I'm going to zoom in here and I say split this point here, split this point, and then split this point. Okay, then throw away this, then throw away that. So I'm going to have this, and I'm going to say, okay, what command I know is loft, surface loft, and it does this lofting, and I see the surface is like that. This actually is a poly surface. It's a lot of tiny little surface and has a lot of tiny little details in it. How can we do to avoid this? It has a lot of tiny grid points, and once you mesh that, I can experiment with that right away, it's gonna, we say using simple mesh, okay, you're gonna get a mesh that is a lot of skinny stuff. This is, you know, asking for trouble right away. So what I'm gonna do is I'm gonna go back, says no, I don't want that. I'm gonna take this, I'm gonna say fit curve. Fit curve is essentially the same thing as turning these curves into so-called free-form curve. So please read up about this, but I'm going to use here the command fit curve, which is here, and it has a tolerance, it has a degree, and it has an angle tolerance, meaning that it takes this object, which is now a collection of tiny little segments, and it turns it into a few simple curves. I really want one simple curve. I'm going to say this angle to 90 degrees, and I'll say finish it. So I obtain that right now, two curves, and let me try to explode them, and oops, they can't explode. They are really simple curves. Very nice. So let's see what we can do with this. I'm going to do a loft, and sure enough, that produces a surface. It's a really nice, clean surface. And when we mesh it, there may be some skinny stuff, but we are not just adding new control. This is a nice, clean surface. That sort of follows the geometry. Of course, it doesn't, if there were some details occurring, this surface sort of bulges sort of in this direction, the loft process would not capture that. So that was our example for loft. Let me go to the next example. I have another loft example which I'm going to stay away from. Patch, that's a very interesting command. So I'm going to bring this another example. Very powerful tool whose power has recently increased substantially with the Rhino 5. It allows us to do things that we could not do before. So here I've created this dummy set of things. What are they? There are a number of polylines. There are a few points suspended in mid-space and a straight line. And I guess I'm asking the very ambiguous question, hey, pass a surface through this. I mean, you ask an ambiguous question, you're going to get an ambiguous response. So I'm going to say surface, and I'm going to say patch, and it says to me, you know, I guess the number of, you know, degrees of freedom in the U and V direction. I say, okay, and it gives me this. It says, this is what you want. Okay, okay, I wasn't expecting this, but why not? This is sort of an average, essentially, through these points on these various things that I gave it. Okay, well, that can be very, very handy. It's obviously not made to capture the details and a sharp corner occurring in there, because it basically approximates that with essentially like approximating a bunch of points with a polynomial, essentially, you know, sort of. So a polynomial doesn't have poles in it. If you have poles in it, you know, in analytic geometry, you cannot capture sharp corners with this, but it's good enough. All right, that's not the one application I am particularly interested in. Is the second one that I find very interesting, which I'm going to bring up right now. And I know it's getting kind of close to the end of the presentation, but I'm going to continue, and I'm going to keep this video, and then you can watch it later if you have trouble with that. In this example, what I'm going to do is that I'm going to select one of these models, one of these meshes, and I'm going to simply select the mesh and say patch, surface, patch. And I say preview, okay, and it basically does an approximation of the surface. Obviously, this is a very lazy approximation of the surface, but maybe I can be a bit more serious about it, and I say patch, and I say maybe use 10 in this and 10 in this, and I say adjust. And the stiffness is essentially how volatile you want, how accurate you want it to be, but then you're losing additional stuff. But I want to say okay. So now I get something, and as you can see by the sort of the marble, or the sort of marbling that you can see here, that this surface is really doing the best it can to approach this mesh very closely. And it has nothing to do with the quality of the mesh. The mesh could have holes, you know, doubly defined things. It's the points of the mesh that are driving this surface. So this is a very powerful thing, and anyone who tells you, wait a minute, here you're not capturing this thing properly, doesn't know that probably this mesh comes from some geological model operator having chosen a certain threshold and, or maybe just 2 points to obtain this surface. So you got to know how you're going to use this. I'm going to move now to mesh patch. Mesh patch, you're familiar with that. This produces a mesh. So it's coming up here. And one thing that I really would like to point out here with regard to this mesh patch is, okay, the idea is that you have a collection of these polylines or curves or whatever it is, and you say, pass a mesh through that. So if I select these things and type this, look at this command here called mesh patch, it will try to extract points automatically from these curves, and sometimes it will take a long time. It will produce a mesh, but it's not good enough. So what I'm going to do here, I'm going to do a preliminary operation whereby I extract points from my object by saying to it to create points every 5 meters. So I put 5, and now it has created for me points 5 meters apart. Now I'm going to say edit, select objects, points, which now I feed to mesh patch, which now produces for me this really nice looking, if I get rid of the grid points here, the points, select points, go away and select objects, curves, go away. You can see that I obtained here something that looks very nice, looks almost like the same surfaces that you see in the geological model. One thing that was very important is that I extracted points from the curves, and the way I extracted these points, is by telling this command called point object divide curve by length, a length that was less than the typical distance in the vertical direction between these isolines. So if I look at the distance here, analyze distance from say here to here, you can see that the z distance is 18 meters. So if you sample these curves at a distance of more than 18 meters, it's going to create this kind of aliasing effect. Basically, it will not see these shelves. So, and it's going to produce a lot of noise. So you want to sample them at a distance shorter than the average distance of this height of these curves, and then you can be sure that you obtain a nice and smooth representation. Drape. This is sort of the silver bullet that we use often. So again, I'm going to, I want to say that that mesh patch is good for contour lines. Don't use the curves directly. Use curve, point object, divide curve by length, etc., etc. Drape. You've seen the drape one very much, and that one is coming up. And in the drape, it's a very powerful tool. Okay, this is the drape thing, and I'm going to go in the top view. Essentially, each surface, each view of Rhino has a construction plane, meaning basically it's that sort of gridded surface that you see in the top. You see here, okay, you see this gridded surface on the lower left corner. That is the so-called construction plane, meaning that if I say project, it will project on that plane. If I say drape, it will drape on that plane. Each view has its own construction plane, and you can move this construction plane around. There are a number of tools that are available that allows you to do that. But here, in the top view, I'm going to go in here and I say, look, turn this object, drape this object. Very simple. Anything you put in there, even solid or anything like that, it's like putting a silk tablecloth on this table. So drape, go from here to here, and I draw a curve, and sure enough, now if I hide the mesh, I see I have created this object, which is essentially a representation of that. If you look at this thing, there are some parameters that defines, you see there's a sort of a structure, an IJ, there's an IJ structure to this. There are, sort of it grids the surface in the east-west and north-south direction. If you make it too fine, it creates unrealistic features on the surface. So there's this issue of aliasing, like the Nyquist criteria for sampling signals. You don't want to oversample. You may have results of it. So don't be greedy. Don't, you make it, make a simple surface, and then later on, if you need more, make it finer. The payback by making simple choices in the shapes is so much more important, so much more attractive. Here I have a very interesting example that comes from me from a couple of years ago from one of my colleagues in Canada, where we want to create a surface out of something that really is like completely not like the surface at all. So I'm going to be more clear here by what I mean. These are some geological beddings. You know, we would like to turn this thing, believe it or not, into a surface. You know, we say this is really kind of like a surface, and we want to kind of turn this object that, yes, it is kind of like a surface. It has a very thin cross-section, but these are actually volumes. You can see that these are volumes. They have a certain thickness to them, but I want to somehow replace that by a surface. How can I do that? Well, I'm going to say, really, what I need here is that I want to take all these points that I have here, including places where I don't have points, just remesh that. So what do you mean by remesh? Meaning just connect them into triangles. Okay, let's do that. So select this mesh. The operation is extract point. Extract point. No. Oops. Extracted points. Okay? So, you know, 400,000 points. Okay. So I extracted these points. The mesh themselves, I'm going to get rid of them. Edit select object. We can keep that. Select objects, polygon, meshes. This is the mesh that we use. There are so many points that the mesh you can't see. So I'm going to hide that. Okay. So these are our points. Now I'm going to tell it to mesh patch. Just as we used mesh patch before. It asks me for some angle tolerances and things like that, but it's very quick normally at creating a triangular mesh essentially obtained through an operation called Delaunay triangulation of this object. So it will create a triangulated object from this cloud of points. But since this cloud of points has so I'm going to bring this up here. So I'm going to throw away all the points that I have because those points take a lot of energy from the computer. So I'm going to take it out. So delete those curves. So what I have is this surface. So it basically said, oh, I'm going to use a very sort of intuitive approach of connecting every point to its neighbors to create a triangle. That is essentially what is called the Delaunay triangulation, a natural, you know, a very natural metric-based way of creating triangles. But if I look at this triangulation, it looks awful. If I look close by, I see that, my God, it looks like a waffle because we had points above and below the surface. So who is close to who, you know, it will connect things all over the place. You can see there, like, if I go in here, you can see that it's like the surface of, you know, the planet Europa. So it looks terrible. So we can't really, this is absolutely useless for the purposes we have in mind for sure. So how can we get rid of this? How can we make this better? Very simple. We select this object and we use this tool called Transform Smooth. And what does smooth do? This is the object that I want to smooth. And smooth basically averages the XYZs of each point with the neighbors. So it's a sort of a filtering process. And fixes the boundary. So we don't want to touch the boundary, but we say do that once. So we say, okay. So let's smooth this thing. Let's look at this thing. It looks a little bit more humane. We're going to smooth that again. Again, smooth, smooth. We're going to smooth that again. As you can see, the grid points move as we are doing that. And the boundary doesn't. Now, sure, of course, we are moving away from the original geometry. But what original geometry? It was just the volume that we are trying to approximate. So I'm going to do that a number of times. You know, you can, you know, I'm going to do a few times this thing, and I'm going to just stop right now, see what this thing looks like. You know, hey, it looks way better. Look, you know, You see, it looks much nicer. It's getting closer and closer. I mean, for ranging purposes, for example, it would be good enough as far as I'm concerned. And in fact, if I bring in now the original surface that we had, and we show these things both together, you can see that the surface that now appears as gray is almost entirely inside the volume that appears in brown. So this is almost a 100% success in terms of an interpretation of a surface that goes through this otherwise very ugly volume. So this approach, which involves using extract point, mesh patch, and multiple smoothing, is what we really need here to create. So to make sense out of these faults, really faults that look very, very awful with multiple faults on top of each other, that's what I would suggest. Okay. So I'm going to move on here. We're gone 5 minutes overboard here. Building hybrid meshes for 3-deck. I've tried to put into one slide everything having to do with hybrid meshes. First of all, we're building hybrid meshes for 3-deck, but we're going to be using Flat 3D to do that. So hybrid mesh means, so again, this presentation is going to probably leave you with more questions than answers, so please send me your questions. But I want to just get you interested that hybrid meshes means a mesh that is stair-step everywhere except near faults, because faults need to function mechanically properly, so we cannot have stair-steps in these faults, whether it's 3-deck or Flat 3D, especially in 3-deck. So what we are doing is that we will create a Flat 3D model that then later on we translate into 3-deck using one of Jim Hazard's fish functions, or whoever has developed things like that. So we first build a fine Cartesian mesh, so using a gen zone, put the 8-node corners. Or, by the way, you can create a nice Cartesian mesh using Block Ranger that at least honors the top topography, and then use that as a basis of your hybrid model. Then we use geometry range within Flat 3D to identify, to tag the zones that are close to these faults, say within 10 meters of these faults. Then we remove those zones and then remesh the space that we have created with tetrahedra. One thing that is important is that we need to make sure that we use a secondary ranging process. And again, if you have any questions, please contact me. I'm going to bring up an example that shows this. What I mean by secondary ranging, means this. This is the model that I created. In Flat 3D, I introduced, these surfaces were meshed, were put in Flat 3D, imported as an STL file. I'm not going into much detail here. These surfaces were triangulated, put into Flat 3D. Flat 3D read them. We used the range command to identify these zones. These zones were inside Flat 3D. These zones, I hid or deleted all the other zones that were outside. So this is the group of zones that is within, say, 15 meters of these faults that you saw before. And I used Flat 3D and I said plot export, and I exported it as a VRML or as a DXF, and now you can read it in Rhino. So I can see it in here. So as you can see, this object, which is really a closed mesh, as you can see, it's a closed mesh, right? Including the faults that goes with it inside it, which will be triangulated, obviously, is a good input surface for KUBRIX, correct? Meaning that you give that as the outer surface and those faults as the fault 1, 2, 3, 4, 5, or all of them as just one fault, and you can run KUBRIX, and KUBRIX will make sure that the space that is in sandwich between the faults and the stair-step mesh will be meshed with tetrahedra. So one thing that is important here is what I call the secondary ranging. So let me talk about that for 1 second here. So I'm going to hide everything else. If you look at this, this is essentially the outer. You see there are some captive volumes in there, some volumes that are in the middle of the air. If I actually took this thing and I said split it's split it into 7 meshes. So let's look at this thing. If I actually colorize it separately, so I'm going to say colorize. So look at this thing. I select this one, I hide it, and I see a bunch of volumes that are in suspension in this thing. And as you can see, what is interesting is that these volumes do appear transparent. It's because their normals is facing inward instead of outward. So for the range logic, these volumes do not belong. But for KUBRIX, there are going to be yet another closed volume. So they're going to be meshed. So once we mesh this core and the faults with KUBRIX, there are going to be zones in here. But these zones should not be here. In fact, in the original FLAC 3D model, those zones remain in the FLAC 3D model. So when I bring in these zones, they will be on top of the other zones. So it will produce double zones in the middle. So that is a problem. So what I do is to range the KUBRIX mesh with exactly this core, this surface that I showed, this DXF surface that I showed you. So meaning that this surface here, which you can use for a ranging process, use this to range the output of KUBRIX, to throw away those zones that have been created with those captive volumes. Now, what remains then will fit right in the original FLAC 3D model to give you a nice mesh that will look like this. So I'm going to move on to the next. So I'm summarizing here in the form of a few slides. These are the faults that we use. So either data files, we create a big brick, and then we import the geometry of the faults. We use a zone geometry range of these faults of 25 meters to create a stair-step mesh. We plot the DXF output. And it's sort of a few gymnastics that you have to do to essentially bring back the part that you saved, etc. One thing that is important, I want to point out, and I forgot, I guess, but now I remember, I should mention that this mesh that you produce with KUBRIX has now in it the face groups, right? You should read this mesh first into FLAC 3D, then read the stair-step mesh of the remaining zones in FLAC 3D to make sure that the node numberings remain constant, and you can actually refer to those face groups. Please contact me if you have any question. I'm limited in time, so I need to move forward here. And at the end, you use the script that Jim Hazard had written for doing this. So the core, as I mentioned to you, and now removing the core is the stair-step mesh. So I'm saying this mesh representing the outside, you should read that after you write the core generated by KUBRIX and ranged by that surface. And then you run KUBRIX with that stair-step mesh as you saw in Rhino. So the stair-step mesh represents the outer volume, and inside it there are all these faults, fault 1, fault 2. They all appear now in KUBRIX 15 with their own dash fault command, so they all become, so if they have, if you have like 10 fault statements here, you're going to have 10 face groups, okay, etc., etc. And you obtain this. So this is the tetra mesh that essentially sits in that stair-step volume. And here's the nice view in the 3-deck model after we translate. You can see in detail what happens. We have a stair-step mesh, that has remained unharmed. These surfaces and the boundary of the stair-step mesh, the volume in between, has meshed this very handsome-looking tetrahedra that, by the way, incidentally, match the grid points. So they often don't create any attaches, which is very attractive. But that's another issue. But anyway, you can see a mesh. That's how it's produced. So in this case, it's a 3-deck model that we produced that way, and I think that to me it's very attractive. Oh, one last thing. I want to absolutely not leave without bringing this up here. One last thing. You need to contact Joe Cheng if you have any question about that, or Ed Zick. But basically, for some of you who have done this thing, there is a competition in FLAC 3D between attaches and between attaches and interfaces. Meaning, when you say interface, you're basically leaving a grid points free to move along another surface, but if it's not attached to its neighbor, it just falls off and producing, especially in caving type applications, accelerated, code blows up. So there's an order in which you do this. I put that here. So when you have face groups, when you use densify, the face groups will be densified with it, which is good. That's the way we want it to be. So first of all, you need to densify that area. Then you need to separate the parts. Then you need to set up the interfaces. Then you need to use the attach using the exclude, by excluding the groups that have become interfaces. So interface ID face group, etc. Attach face range group face 1 not. So I know this is very cryptic and very, very fast, but I want to bring your attention that if you don't do that, you're going to run into trouble now that we're doing really sophisticated stuff that involves attaches and interfaces. If you have any information, if you have any question, or if you see that this system is causing you trouble, please contact Joe Cheng, and we're going to figure this out. Thank you very much, and give me a call or email me, and I would be glad to answer your questions. This will be available as a recording in a matter of a few days. Bye-bye.